Okay, so we're going to start off by talking about some examples illustrating the concepts of openness, closedness, and boundary, interior, closure, etc. Our first example is concerning open intervals in R. So what we want to do is we want to show that open intervals of the form A comma B actually are open sets. And so just as a reminder, what does it take to be an open set? Um, so what I'm going to do here is, sorry, I'm just going to do a sketch. What you should do at home is you should do a formal proof. Okay, remember for our formal proof, we have hypothesis, claim, and then start off with the proof. Okay, so let's see why
it's 10 hours.
Thank you. Let's see why is this true. So suppose I have an open set, an open interval AB. So this interval is open in R if and only if it is equal to its interior, right? And so what does that mean to be equal to its interior? So remember, E is open if and only if E is equal to its interior. And we know that always the interior of a set is contained in the set. So if we want to show that E is open, this is true if and only if E is a subset of its interior. Okay? So what we need to do is we need to show that if X is a point in AB, then X is in the interior of AB. And now what would it mean to say that X is in the interior of AB? Well, that means that there exists some R greater than 0 such that the set of, we can say T and R, such that the distance between X and T is less than R. This set needs to be, so this set right here should be a subset of AB. Okay, so if I'm just looking at it here, so here's my A, here's B, and suppose I have X. My question is, how am I supposed to show there exists an R such that the R ball is contained in AB? And from this picture, it looks like perhaps I choose R to be X minus A or X minus A over 2. The problem though is, imagine if X is actually closer over here, right? Then, in this case, I want to choose R to be B minus X, right? Because then, if R is B minus X, I'd be looking at all of these points here. So to get around that, basically what I want is I want R to be the minimum of the distance between X and B, which would be B minus X since B is bigger than X, and the distance between X and A. So that would be X minus A. Okay, so for this R, so we'll say then, number 1, this R is greater than 0. And number 2, the set of T such that the distance between X and T is less than R is contained in our set AB. Okay. So for instance, when you're doing your formal proof, right, with hypothesis, claim, and proof, you would need to show these two things, right? So you need to show that R is greater than 0, and you would need to show that this set is contained in AB. Okay, you also could use R to be those numbers over 2 or anything smaller. Okay, so there's a reason why we call these sets open, right? So when we say it's an open interval, it is actually referring to open in a topological sense. Okay, our second example also involves real numbers, and we want to show that when we talk about closed intervals, right, they are closed in a topological sense. Okay, so the first thing we want to show is that closed intervals are closed sets, and then we're going to show that the interior of the closed interval is this set AB. Now, for the first one here, so part one is to discuss that closed intervals are closed sets. So if I want to say that this is a closed set, what's the definition of a set being closed? Remember, E is closed if and only if its complement is open, right? So if I want to show that this interval is closed, I need to show that its complement, so the points in R that aren't in this closed interval, is open. And now, what is the complement? So the complement would be from negative infinity to A, union B to infinity. And now, all I would need to do is show that all I would need to do is show that sets of the form B infinity and negative infinity A, sets like this are open sets. So back here, when we were showing that open intervals are open sets, we're assuming here that A and B are real numbers. If I could extend this, which you can, you could extend this to consider unbounded open intervals. Then we can show that these unbounded intervals, open intervals, are open sets. And then the second thing we would do is we would say that the union of open sets is open. Right, so this would be like fact 1, and then this would be fact 2, and then 1 plus 2 would imply that AB is closed. Right, so 1 plus 2 would imply that AB is closed. Right, or we could call this 3, this definition here, so we'd have 1 plus 2 plus 3. Okay, now the fact that the union of open sets is open is part of the, I think that is the second proposition that we mentioned in class. So that's yeah, that was part of a proposition that we stated in class. It was the last part, which is that the union of any collection of open sets is again open. And so I'll leave for you as practice to prove that unbounded open intervals are indeed open sets. And then that would prove that closed intervals are closed sets. Now let's look at showing that the interior of this closed interval is AB. Add a page below. Okay, so I want to show that the interior of this closed interval is equal to the open interval. That's what I want to show. Now, what does this mean? Well, we know that the interior of AB is a subset of AB, right? So if we are saying that the interior is equal to AB, here's what we would need to do. We would need to prove that number one, A is not in the interior of AB. Number two, B is not in the interior of AB. And then number three, right, X belonging to AB implies X belongs to the interior of AB. So this third bullet point is essentially, this third bullet point is proving that AB is contained in the interior, is a subset of the interior. And the first two, right, since the interior is a subset of the closed interval, these first two are proving that the interior is contained in the open interval as opposed to the closed interval, right? Okay, so just as a sketch, how would we prove, this is a sketch for number one, how would we prove that A is not in the interior? Well, let's go back to the definition. A is not in the interior of AB if and only if for every R greater than 0, it is not the case that our set, that R ball is contained in AB. Right, and remember the R ball, these are the points that are within R units of A. So these are the T and R such that the distance between T and A is less than R. So what this is saying is, so here's A, and then here's B. So we're saying that for every R, regardless of your choice of a radius R, doesn't matter how small you try to take R, right? So here this would be a small R. This set, so this set here are the points within R units of A. And this is true because we'll always have some points that are within R units of A that are outside of our interval, namely any point that's less than A, right? So here's what we could do. So we could say fix R greater than A, sorry, R greater than 0, and then we'll show you that there exists a point within R units of A which is not contained in that closed interval. Okay, so we'll say fix. So our claim is that A does not belong to the interior of the closed set AB. Hypothesis is just that A and B are real numbers. And so here's our proof. Fix R greater than 0. Then, okay, so if we draw this, here's our A, and R is fixed. So we've got R plus A, R minus A. And what we want to say is, by the density of real numbers, there exists a Q in between A minus R and A. So Q is in between A and A minus R. For that Q, Q belongs to, let me put this one in a line. So for that Q, Q belongs to the set of T and R such that the distance between Q and A, or sorry, the distance between T and A is less than R. But since Q is less than A, Q does not belong to A intersection, the closed interval from A to B. So the set of T and R such that the distance between T and A is less than R is not contained in AB. Since this is true for any positive R, A does not belong to the interior of AB. Okay, so that kind of shows you how to prove this first one here, right? How to give a formal proof, and then the proof for B is going to be very similar. You'll just use the fact that instead of going to the left, right? So here you'll say for every R greater than 0, let R greater than 0 be given, and now use the density to show that there exists a Q in between B and B plus R. This Q is not going to be
15.
Thank you. This Q is not going to be in our interval, but it is going to be in that R ball around B. So it's not the case that we can find an R for which that R ball is completely contained in AB. Okay. And then lastly, here, this AB, so to show number 3, which is that if X is in the open interval AB, then X is in the interior. Well, we can do that actually kind of piggybacking on what we had from before. Add a page below. Because we know that if X is in AB, then we know that there exists an R such that the set of T in R with the distance between X and T less than R, we know that there exists an R ball centered at X, which is contained in AB, but now AB is contained in AB, right? So we can piggyback off the fact that the open interval AB is open to show that the open interval AB is contained in the interior of the closed interval AB. And this reasoning shows you the same reasoning implies that for any metric space SD, right, if E and F are subsets of S and E is contained in F, then the interior of E is a subset of the interior of F. Okay, so this is something that would be an easy exercise, should be an easy exercise to verify. Okay, so we're done with that example. And now let's look at example 3, which is to say that the boundary of the closed set is are the points AB, and the boundary of the open interval AB is the set of just 2 points AB. So again, we'll just do a sketch here. So let's look at now, so we're going to let E, because I think that this notation is kind of confusing. So I'm going to say let E equal, or let E be defined as this closed set AB. Okay, so we know that the boundary of E is, by definition, the closure of E, things in the closure of E that aren't in the interior of E. Okay, now if E is the closed set AB, then the interior of E, we already showed, is the open interval AB. And since E is closed, the closure of E is equal to E. Now, why is that? Remember that the closure of E is the intersection of all closed sets containing E. So K is closed and K contains E. Right? So always the closure contains E is always a subset of its closure. Does that make sense? Because E is a subset of every K. So this would be something for you to prove. So verify. Oh, sorry. Verify. So we'll do this. Verify for any metric space SD. If E is a subset of S, then the interior of E is a subset of E, and E is a subset of the closure of E. Right, so you should verify that. Okay, so always the closure of E is a subset of the closure of E, but if E is closed, then we have to have this intersection is a subset of E because E is one of the K, right? So you get what I'm saying? So here's another fact. Always, if you have the intersection of some sets, A sub alpha, and alpha is in some kind of index, this is a subset of A beta, and this is true for all beta in your indexing set, right? So your intersection has to be a subset of each one of the sets that you're intersecting. Make sense? Okay. And each one of the sets has to be a subset of the union of the sets that you're unioning. So since E is closed, it is equal to its closure. All right. So if we know that E is equal to its closure, now the boundary is just going to be the points in the closure of E that aren't in the interior of E, and that is going to be the points A and B. Okay. Now, the next thing is I will leave it to you. It'll be good practice for you to prove, to give a formal proof of this first one here. And then for the second one here, prove this, right? So prove that the boundary of the open set is AB. Part of that is going to require you to find the closure, right? So you're going to have to prove the closure of AB is equal to this closed set here. So that would be step one, would be to prove this. And then you already know the interior. And so then it should follow with similar computations to this right here. All right. And then lastly, just to point out that in RK, so in Euclidean space, the open balls, so these open balls are open sets. Let's see here, the most we can draw is K equal to 3. And this is saying, like, suppose you have some point X naught. Now, if you look at the R ball, which would be a radius of, right, so this R is your radius of this sphere. And now, if you don't include these points that are exactly R units away, so notice this is a strict inequality, then you have an open set. If you do include, right, the boundary point, so you're saying less than or equal to R, then we're looking at a closed set. And then lastly, the boundary of each of the open ball and the closed ball is the shell. So the boundary is the shell, if you will. So the shell, the set of points where the distance is exactly equal to R. Okay, so for instance, for K equals 2, if we have some point X naught, we can talk about the points that are within R units from X naught, right? So that's an open set. Now, if we include if we include the points that are exactly equal to R, so if we include that circle, now we've got a closed set, and then the boundary is just the circle itself. So we would have to do that. Okay. So the boundary would just be the circle. Okay. All right, so that is it for our examples.